Hi, and welcome to AI and Machine Learning with Polyolygon. I'm Mavis Ledford. This is the second of several nascent technology presentations we'll be doing for post-secondary. The first topic, AR and VR, was more blue skies in terms of current higher ed utility, but we'll find today's topic on AI and machine learning quite the opposite. Before we dive in, let's restate what we're aiming to take away from these technology presentations. One, to give the post-secondary team a high-level overview of these technologies for good general working knowledge. Two, to share insights into how these technologies in AI are leveraged today in higher education. And three, to evaluate opportunities to leverage these nascent technologies to meet post-secondary specific goals. So what is artificial intelligence? AI is an area of computer science that equips computers with cognitive functions, which we normally associate with human intelligence, like learning and problem solving. It's an unassuming definition, but of all the emerging technology topics we'll be covering, we find AI will be the most impactful, not just for education, but for our lives in general. And it's not because of these super intelligent robots from science fiction. Sentient machines actually fall under a branch of AI called artificial general intelligence, which is still more research and theory than anything else. The technologies discussed in this presentation, and practically all AI technology today, fall under the scope of narrow AI. AI designed to solve singular problems or tasks extremely well, often better than human specialists can, despite not actually having consciousness. For example, this is a screenshot of a student texting an AI chatbot to help him fill out his FAFSA forms for federal student aid. It runs 24 hours a day and can handle hundreds of students at once. This chatbot, named Pounce, uses a form of AI called natural language processing to understand and respond to requests. NLP is one of several main branches of artificial intelligence, from robotics to vision. We'll be focusing on just the branches with the most direct application to higher ed, like expert systems and, most importantly, machine learning. Machine learning plays such a significant role in AI that major periods of AI development are often defined by it. Long before we had the broad set of AI fields we have today, the concept of applying intelligence to computer tasks had its start way back in the 1950s. By the 80s, machine learning reorganized as its own subfield and really started to flourish by utilizing methods and models borrowed from statistics and probability theory. The third and current period of AI only started around 2010 when a subfield of machine learning called deep learning became practical. This field is not to be confused with education's deeper learning pedagogy concepts, and it's a major driver of the AI boom we're experiencing today. Three components were needed for this boom to happen. First, we have the data model. Today's advanced algorithms, particularly in deeper learning, gives AI the ability to solve diverse problems too complex for human coders. Next, we have big data. These new data models require massive amounts of data. Thanks to our modern digital infrastructure and cheap, abundant data storage, we now have those large-scale data sets. And finally, processing power. Big data isn't effective without an efficient way of processing it, and the parallel processing power of today's graphic cards and network cloud computing makes it all possible. Today, even a regular individual can leverage these new machine learning technologies on the cloud, as cloud computing providers like Amazon Web Services and Microsoft Azure have integrated machine learning as a service into their cloud offerings. And there's an ever-expanding list of free and open source machine learning software as well. Most of these open source machine learning frameworks have actually been released by pioneering institutions like Carnegie Mellon, NYU, and UC Berkeley. Universities continue to spearhead much of this technology. On the right, we can see in dark blue that 40% of all AI patent assignees in 2016 are coming from academic sources. Today, AI technology can be found all around us. For example, if you've ever used voice assistants like Siri or Alexa, these leverage natural language processing and deep learning for natural sounding voices. If you've ever had Facebook automatically suggest a photo tag, that's using DeepFace, Facebook's deep learning facial recognition system. And if you've ever done a Google search, it's been utilizing a machine learning AI system called RankBrain since 2015. Google in particular has been a big proponent of AI and has over 4,000 projects harnessing machine learning. You can see that back in 2012, only 5 years ago, they had 0. Now it's leveraged in most Google products, from Android and Chrome to Maps and even Cardboard. Another pioneer in machine learning is NVIDIA, who produces graphic cards utilized heavily in this field. They've noted explosive interest across industries, with higher ed notably on that list. Now let's take a closer look at that big important piece of AI, machine learning, and its offspring, deep learning. Machine learning is often thought of as a mysterious black box full of answers, but you don't need a technical background to understand how it works. Getting familiar with the conceptual parts should be helpful in assessing its use in higher education, and we won't need to get into any esoteric computational details to do that. From a theory perspective, a good comparison is to how humans learn. Traditional computer programs simply follow coded instructions like an advanced calculator. If X, then do Y, while human brains learn from experience. But with machine learning, computer programs learn from experience too. That experience is called data. Let's look at an example. Let's say we wanted to create a machine learning formula that detects when students are at risk of dropping out, a common use case for retention solutions. If we had access to enough historical institutional data for past students pulled from their SIS, LMS, transcripts, and related sources, we could test that data through the right machine learning algorithms until we found a valid set of predictors to accurately forecast future at-risk students. The formula machine learning generates for us could find the common denominators between combinations of courses, missed days, excessive credit hours, financial issues, or even particular dorm halls to be determining factors of at-risk students. You might ask, wait, doesn't that sound a lot like predictive analytics, using historical statistical data to predict future outcomes? And you'd be right. Machine learning uses statistical algorithms to make high-end predictions on data, just like other forms of predictive analytics. Machine learning, however, has much broader use cases than just predictive analytics, and when used in this way, it can be considered a pioneering technology in predictive analytics with a host of advantages. Most significantly, machine learning is all about generating accurate, reusable predictive formulas automatically through data training. In this case, our institutional records are passed through a specific machine learning algorithm picked by data scientists, which generates a predictive formula unique to the patterns and cases in our data. The solution is automatically written down into a self-contained formula called a machine learning model. And data scientists don't have to rely on making these predictive formulas from scratch. That workflow is streamlined too. They tap into an extensive field of well-documented, task-based machine learning algorithms organized by type of solution. These are the generic formulas data scientists train test data against to automatically generate our data-trained machine learning model formulas. Once created, these machine learning models behave like self-contained logic components within an application. This is a pretty powerful concept. This reusable formula can be duplicated, distributed, and deployed in numerous applications, including on mobile, making accurate predictions against new data without having to be tied to data warehouses. Google demonstrated the power of this when they released MobileNets this year, a series of mobile-optimized vision models that allowed applications to detect objects, faces, and features in photos even without an internet connection. This is something that previously required cloud-based APIs or a powerful machine to do. The workflow for creating a machine learning model looks like this. A raw data set is pre-processed into structured data. This just involves formatting it into labeled columns, similar to a spreadsheet. This uniform structured data is then processed through a machine learning algorithm in a step called training. This training process usually requires thousands or sometimes millions of quality data entries to generate an accurate predictive formula for future data. That accurate predictive formula is our golden model, which is then integrated into the final application to be leveraged with new data. This model can be further updated and tweaked over time as algorithms are improved and more training data is acquired. Okay, we've discussed how the magic of machine learning works. Now what about its offspring, deep learning? As we mentioned, deep learning is a subset of machine learning that has really taken off in the last few years. Deep learning was originally inspired by the way neurons work in the brain, so its methods are aptly named neural networks. This was actually an old AI concept, but modern techniques moved it out of the realm of novelty when they significantly scaled up the network layers and the amount of data pushed through them, hence the overarching name deep learning. That scaling up turned out to be a major breakthrough, enabling many of the innovative applications of machine learning we see today, like natural voice assistants and self-driving cars. Google's AlphaGo recently showed off the potential of deep learning when achieving a goal that many experts predicted was still a decade or more away. This year, it beat the human world champion at the ancient Chinese board game Go. Unlike chess or checkers, Go's huge 19 by 19 board and nearly unlimited moves make it impossible to use pre-calculated AI strategies that look at every single combination of moves. So the best computer programs written by humans only manage to reach amateur levels. AlphaGo built its own winning strategy by analyzing tens of millions of past Go matches and by playing against versions of itself millions of times to continue to hone its own decision making. Go requires intuition and creative strategies to win, and that's what AlphaGo developed through a combination of algorithms supported by deep learning methods. So how does deep learning work? The best way to understand it is to contrast it with traditional machine learning. Let's look at this comparison in the next slide. In traditional machine learning, a human evaluates source data and performs a feature extraction step. That's a fancy way of saying that she reviews the collection of historical data and determines the most meaningful fields or predictors to use. Our human then finds the most suitable machine learning algorithms to use with these predictors and tests her hypothesis, usually by trial and error, until a good combination of data predictors and algorithms are selected to create the most accurate predictions she can find. In short, traditional machine learning uses hand-tuned features processed through hand-picked algorithms. But like Go, not all problems are so cut and dry. Sometimes we don't know what's important in our data, and sometimes complex problems don't fit in our traditional task-specific algorithms, or sometimes they require multiple combinations of algorithms too long and complex to hand select. That's where deep learning excels. It processes raw big data sets to discover its own features that best represent the problem, while iterating on the solution at the same time. Our human doesn't even have to format the data, let alone define data features. There are many types of neural networks that behave differently, but in general, deep learning does this strictly by using concepts and data representation itself to find the patterns in complex data. It processes the data through cascading layers of processing units called nodes, transforming the data at each node and identifying relevant features of each layer until the full solution emerges. One of deep learning's biggest advantages is that the more data you throw at it, the better it performs. They're designed for and excel with massive data sets. And when it comes to predictive analytics with big data, the incredible predictive power of deep learning's neural networks can't be overstated. For example, in 2015, a research group at Mount Sinai Hospital in New York trained a deep learning network on the hospital's vast database of 700,000 patient records with hundreds of variables per patient. The resulting program, dubbed Deep Patient, was able to predict a wide range of ailments on new patient records, including the onset of schizophrenia. Researchers still don't know how the AI researched its conclusions, only that they were accurate. Which also leads to the biggest criticism of deep learning. Its self-generated solution formulas are almost impossible to interpret since they involve countless layers of complex mathematical transformations too numerous to follow. This leads to the philosophical question, can we trust incredibly powerful predictive models to make important decisions if we can't understand the rationale behind them? On the other end of the spectrum, a simple machine learning formula can also be inappropriate due to its lack of nuance. Interpretability versus predictive power can be a major trade-off in predictive machine learning, with deep learning truly being a black box option. But as mentioned, predictive analytics is just one solution deep learning offers. Deep learning can be applied to unstructured data like text, sound, and images, allowing researchers to contribute diverse breakthroughs to other fields of computing and AI itself, from speech and vision, natural language processing, to machine translation and chatbots. Deep learning's neural networks enable many practical applications of machine learning and by extension the overall field of AI. Okay, interesting stuff. Now let's look at how AI and machine learning technology impacts higher education, specifically in our post-secondary solution areas. As post-secondary experts, you're already familiar with the solution areas themselves, so we'll be focused specifically on the AI-driven companies and technologies impacting them. In our digital learning tools and courseware solution area, we have adaptive learning technology platforms powered by learning analytics. Early and entry-level adaptive learning technology products tend to focus on determining the learner's pathway based on simple criteria, such as the answer to a multiple-choice question. They're often based on underlying linear models that are too simplistic and not truly adaptive. More advanced tools utilize artificial intelligence methods for adaptability that looks more like this. These systems are increasingly dependent on large-scale collections of learning analytics outside of the actual learner. With more data, we expect to see greater capitalization of machine learning models and potentially even deep learning, which should make these products more effective. Here are a few noteworthy adaptive learning platforms. Companies such as Acrobatic, Cogbooks, Realize It, and Smart Sparrow have all been working to prove adaptive learning's viability, where instructors can build adaptive courses using their own content, thus making the course more of a personalized learning experience. I've highlighted companies that the Gates Foundation have already made grants to in yellow, and companies that have been acquired in pink. Alex was acquired by McGraw-Hill in 2013, and Area 9 was acquired by McGraw-Hill in 2014. Of all these digital learning and courseware platforms, Alex is the oldest and longest running. It started in 1996 and is one of the first to utilize big data to ascertain and implement efficient curriculum paths for individual students. Acrobatic is among the newest platforms, first released in 2013. Its smart author platform generates real-time predictive learning estimates for each student against every outcome in the course. You can see it giving more questions on the left to those struggling, providing more guidance. You should have an additional document detailing each company's location, investment rounds, and content models along with this presentation. Contact us for a copy if you don't have it already. Our second post-secondary solution area is Technology-Enabled Advising. This category in particular is incredibly well adapted for the solutions that AI's machine learning models can provide. Boston-based AdmitHub is worth a big mention. They advertise themselves as conversational AI for college success and run the Georgia State University's chatbot we mentioned earlier in this presentation. Not only do they support FAFSA assistance, but also everything from orientation to immunization to transcript submission. Not to be outdone, Deakin University partnered with IBM to be the first worldwide to implement Watson Engagement Advisor, a student advisor application version of IBM Watson. Watson is integrated with their platform DeaconSync, with students reportedly asking up to 1,600 questions a week to learn the ins and outs of life on campus. AdmitHub and IBM Watson are great examples of the indirect benefit of deep learning, which has reduced word errors in speech recognition by 30%. A core staple of the Foundation's work in this area is promoting IPASS, or Integrated Planning and Advising for Student Success platforms. As you know, these platforms utilize the power of predictive data analytics against institutional data sets to promote student success in 4 key areas: progress tracking, student planning, advising and counseling, and early alert systems. Many IPASS platforms like Civitas market on the sophistication of their predictive modeling. In most cases, these are machine learning models that are leveraging known algorithms with their own custom classification techniques. These models are garnering some impressive outcomes. For example, Civitas states 14% of at-risk students are correctly identified using traditional GPA-only risk detection, where 83% of at-risk students were correctly identified using their models. One question is, will IPASS products leverage the next level predictive power of deep learning? These platforms are already able to leverage an ever-expanding anonymized data set of analytics every time a new institution signs up, so it would make sense. However, many machine learning analytics-based companies are already battling the stigma of black box predictions, so if they're using them, they don't seem to advertise it. For example, Civitas's portal for their Student Insights engine contains this quote explicitly stating their solutions are not a black box and you won't have to take their word for it. No matter how powerful the algorithm, data science must still show proof to the institution for the moral imperative of knowing. Companies like Civitas often do this by giving upfront visibility to their list of predictors, those data features we mentioned earlier. This is pretty critical as we know that academic stats are not the whole equation. Civitas, for example, has noted that 99% of institutions in their examples were losing more students above 2.0 GPA than below it. The best predictive models today often include psychosocial contributing factors. Now let's discuss PS Solution Area 3, Finance and Financial Aid. Both AdmitHub and NextGenVest are text-based chatbot startups for helping students with financial aid. As previously discussed, AdmitHub is way more robust, supporting a lot more subjects other than finance, while NextGenVest sticks with student loans and financial aid. NextGenVest has a concept called Money Mentors that send deadline reminders, answer financial aid questions, curate scholarships, and more. Though they also use trained college students, NextGenVest says they leverage machine learning and deep learning to scale personalized communication for Gen Z. Lastly, let's look at some ways AI and machine learning are leveraged in developmental education products. Carnegie Learning's Mika is an intelligent tutoring system for DevEd math. Mika teaches remedial courses for incoming college students, giving a one-to-one tutoring experience. Mika delivers hints and just-in-time feedback to each student based not only on what a student knows, but also on the specific strategy a student uses to solve a problem. One noteworthy field of AI that's making its way into education is expert systems. Also referred to expert context advisors, expert systems are a computer system that emulates the decision-making ability of a human expert. They rely heavily on the AI field of natural language processing for concepts like automatic speech recognition, sentiment analysis, entity extraction, natural language generation, and of course, question answering. Our previously mentioned IBM Watson is the best known expert system. It's a question answering computer system capable of answering questions posed in natural language. The most practical impact has been in the medical field, where IBM's Watson for Oncology application helps diagnose cancer and suggest treatments together with physicians. In research, the IBM Watson Discovery Advisor has aided a research team to analyze more than 70,000 articles for proteins linked to cancer. In healthcare, 90% of nurses in the field who use Watson now follow its guidance. And in education, IBM is currently working with both Pearson and Blackboard on leveraging Watson for one-on-one AI tutoring in their products. While on the topic of AI tutors, another relevant field of AI is affective computing. Affective computing technologies sense the emotional state of a user via sensors, microphone, cameras, and software logic, and respond in kind. For example, by recommending an activity that better fits the mood of the learner. The idea is to create context-aware, emotionally responsive machines that cater to even the most subtly communicated needs. Combined with online learning AI systems, a computerized tutor can react to facial indications of boredom from a student in an effort to motivate or boost confidence. In the same vein, Lenovo's Air Class is a new distance education and training platform that uses webcam-based emotion detection and emotion analytics as one of its core features. Affective Apdex is another company focused on real-time learner emotional responses to educational content. Affectiva markets its technology as Emotion AI, using deep learning capabilities on an emotion data repository of nearly 4 million faces from 75 different countries. They're currently looking for educational partners to collaborate with on the next generation of emotionally aware education solutions. On the other end of education, artificial intelligence can play a key role in better connecting education systems and labor markets. Improved pattern recognition can pinpoint skill sets and traits that would enable someone to be successful in a job and surface insights that have previously not been used. This can help detect promising candidates with less conventional credentials and free us from using school reputation as a proxy for assessing potential. AI can also be used by governments to forecast detailed job market demand more accurately and steer educational institutions to adapt their curricula and approaches accordingly, making sure students have the skills required to fill those jobs. Saudi Arabia is currently exploring using machine learning in this way. Now that we've learned about how AI and machine learning is impacting higher ed, let's discuss some AI-related challenges. Access to high-quality training data is critical for products that use machine learning as a core technology, and that's no different for higher ed. Challenges for higher quality data not only include a lack of quantity, but data bias, that is, data lacking good representation or missing the right metrics. Like other forms of predictive analytics, machine learning algorithms are only as bias-free as the training data presented to it. For example, in this controversial test from Shanghai Jiao Tong University in China, researchers used a variety of machine vision algorithms to study the photo IDs of around 2,000 criminals and non-criminals. Researchers then found their neural network could then correctly identify criminals and non-criminals with an unsettling accuracy of 89.5%. But look at these representative examples used. The dataset is biased, with no smiling white-collar IDs in the criminal set. The algorithm weighed heavily on clothing, which would include socioeconomic factors and subsequent biases inherent in prison populations in this absurd objective. Keeping those biases in mind, in order for big data to be really effective, the dataset must be bigger than most institutions can collect on their own. Good datasets, however, are usually proprietary and hard to build, and that's no different for higher ed. Since owning a large domain-specific dataset can be a significant source of competitive advantage, we can see a tendency for competing companies to keep data private. An example of this can be seen in the nonprofit PAR framework. Many institutions have created data sharing working groups to promote the sharing of anonymized student success analytics across member institutions, and the PAR framework was one of the largest, combining data from hundreds of campuses and containing millions of student records, along with a predictive analytics framework to support it. Hobson's acquired Starfish Retention Solutions in 2015 and then the PAR framework in 2016. They combined the two into the Starfish Enterprise Success Platform. The previously nonprofit PAR had spun off from the Western Interstate Commission for Higher Education, a Gates Foundation-funded nonprofit. It now remains to be seen how Hobson manages this heritage and if it continues to be a competitive advantage over commercial competitors such as Civitas Learning, who independently grew their own dataset. An ideal place to look for the big data required to power good predictive models is a centralized higher ed infrastructure. But this is how the infrastructure exists today. It features inconsistent, incomplete, and often conflicting metrics siloed off between a series of disconnected systems. These systems were created at different times for different purposes, and the metrics published today often only include traditional student metrics in their datasets, which ignore the new normal in higher education, new majority students. As published in the Foundation's Post-Secondary Success Advocacy Priorities, this is what the recommended National Post-Secondary Data System would look like: a central collection of modern key performance metrics for all students in all institutions. If modern data scientists could get access to data like this, they could find patterns and answers to questions we haven't even asked yet. The Foundation has partnered with the Institution for Higher Education Policy, IHEP, to develop a version of this framework with consensus metrics from leading institutions and other Gates-sponsored organizations. These metrics have a special focus on underserved populations who constitute 2/3 of higher education enrollments but are missing or obscured in current higher ed performance measures and public databases. The new National Post-Secondary Data System has been difficult to put in place as data sharing, privacy, and security are not yet governed by a coherent set of policies. They also present ethical issues, starting with who owns data on students, who can see it, who can use it, and for what purposes. Meanwhile, IHEP and its Post-Sec Data Collective of more than 40 partner organizations continues to publish policy papers and promote evolving student-level data legislation, including an interim step of enhancing the utility of existing data systems. This includes the Integrated Post-Secondary Education Data System and National Student Loan Data System. The growth of artificial intelligence promises benefits, but also poses some urgent challenges to jobs as well. The World Economic Forum recently projected that automation will eliminate at least 5 million jobs worldwide by 2020. Factoring AI automation in skills training is becoming more critical as AI technology becomes more ubiquitous. The workforce needs to be reskilled to exploit AI rather than compete with it. For students, a future-focused curriculum is a necessity. The World Economic Forum identifies 16 skills that are needed in the 21st century, including creativity, collaboration, initiative, and adaptability, but those are not included in standard curricula. Lastly, let's talk about opportunities in leveraging the data science community. There is now a large, thriving data science community actively solving complex problems with machine learning and deep learning. Kaggle.com, which was acquired by Google, is one of those communities that feature major algorithm challenges sponsored by companies, organizations, and even the US government. Of the 17 active competitions underway, the largest is a passenger screening algorithm challenge by the US Department of Homeland Security. The TSA is challenging the broader data science community to help improve the accuracy of threat prediction algorithms using datasets of images collected from their scanners. 242 teams are currently competing for $1.5 million in prize money. We see this as a great potential avenue for the Foundation to tap into the broader data science community to potentially contribute solutions for our complex problems in higher education. With a single challenge grant contest, we could have hundreds of research teams crunching our data to find effective machine learning predictions and solutions. We close with Gartner's 2017 Hype Cycle for Artificial Intelligence, where you can see many sub-branches of AI technology we discussed today, such as expert advisors, predictive analytics, and most significantly, machine learning are trending. Gartner estimates 2 to 5 years for these technologies to hit mainstream, but as you can see, they are, in a large part, already here, powering the advanced algorithms inside our phones and websites. Though AI like machine learning and deep learning are already starting to make a big impact in the education space today, improvements in data standards, collections, and data privacy are probably the single biggest roadblock for AI to completely transform the education space. It is sure to happen sooner than later. Thanks for watching our presentation. Questions, comments? Reach out to us at mavis@polyolygon.com and mark@polyolygon.com.